Hello, welcome to the second tutorial video on complex numbers. So if you are new to my channel, kindly subscribe for more videos in the future. Okay, let's start. So in our previous video, we learned how to add complex numbers, divide complex numbers, and also multiply complex numbers, and a group of numbers that are complex numbers. Okay, so like any other number system, for the Cartesian plane, for number system, for complex numbers as well, we have its plane. Okay, so the plane is what we call the Argon diagram or the Argon plane. Okay, so in the Argon plane we have opportunity to plot our complex numbers. Okay, so in our previous video we said, let's say if you have a complex number z being equal to say 1 plus 2i, then this is our complex number, right? So in the Argon plane we can plot the whole of this complex number z, and so the Argon plane looks like this. It's the same as the Cartesian plane. Okay, so you have this, and this will be the imaginary axis, and this will be the real axis. So in other words, most people prefer to call it x and y, like we know from normal Cartesian coordinates. Okay, x and y. All right, so I can quickly call it s and y, and then we continue like that. Okay, so like I said, in the complex numbers, let's say this is our y, this is our x, but mind you, they are not just x and y coordinates, they are the real and imaginary aspects. Okay, so this will correspond to the s coordinates, and this will correspond to the y coordinates. So if I want to plot this complex number z on this Argon diagram or Argon plane, then I have to locate on this x-axis. I have to just give them I have to calibrate it. Okay, so in the calibration I have 1, 2, 3, 4, and the rest. Okay, so with this one too, I can call it 1, 2, 3, and let's say 4. Okay, so if I want to plot 1 plus 2i, it's 1 on the real axis, which is 1 on the s-axis. Okay, and the 2 on the imaginary axis. So I just locate 1 and 2 where they meet, and this will be my complex number z. Okay, I hope you're okay. So in other words, if I want to plot z equals 4 plus, let's say z equals 4 plus, let's say 3i, then it means I have to find 4 on the x-axis or the real axis, that is this side, and just plot find 3 on the imaginary side. Okay, this side. Okay, so I just know where they meet, and I'll plot it. This is let's say this is z2 and this is z1. Okay, so this is z1, this is z2. I hope you are okay. So this is how you can plot complex numbers on the Argon plane or Argon diagram. Okay, so that is it. Okay, now with this, then this means that I can actually look at the complex numbers in the magnitude and the direction or the angle that it makes with the x-axis. Okay, so let's say I have an Argon diagram like this, or Argon plane like this, and this is our x-axis, this is our y-axis. Okay, let's say there is a complex number named z equals 2 plus I, let's say this. Okay, then here is 2, and let's say here is 1. Okay, that is the imaginary aspect. Okay, so it means that this is where they will meet, and this will be our z. Okay, so if you want to know the length of this complex number z, then from normal Cartesian coordinates, what we know, we just draw the actual length is the distance from the origin, the distance from the origin, okay, to the complex number. So we just move to the origin like this, and if you want to know this, what do we do? This, you can see that there is a Pythagoras triangle here, because if this is straight if this line is straight like that, okay, let me use another pen. Okay, let me use another pen. If the line that we are talking about, let's say Z is here, and if the line is straight, okay, then we can draw another line here and the line here, okay, so that we will form this Pythagoras triangle, okay, right angle triangle, with this being the angle theta, so the angle that it makes with the x-axis. And here will be what? Here is the same as this side because they are parallel, and it means that is the length that you will travel from the origin to the imaginary part, okay, and this side from here to here will be the length that you travel on the real part, okay. Then here would actually be the length of our complex number, okay. So from Pythagoras theorem, then it means that the length of our complex number z, that is absolute of z squared, is equal to s squared plus y squared, okay. Then this implies that the length of the complex number is actually equal to square root of s squared plus y squared, where our x and y are this side and this side, okay. So now for this complex number z, then it means that length of z is what? Square root of 2 square, which is 4, plus the imaginary component is what? 1, so 1 squared is what? 1, and this will be what? Square root of 5, and that will be the length of this complex number. I hope you are okay. Okay, so let's move on and know more about the Argon diagram. Okay, so from what we just learned, we said that the complex number can be represented in the Argon plane as this, okay, where this will be a angle theta that it makes with the x-axis or the real axis, and this is our y, and this will be the length, okay. So now if I want to find, if I have a complex number z given as a plus bi, okay, then we know that the magnitude of the complex number or the length of the complex number is the square root of what? The real power squared plus the imaginary power squared, okay. Now with this, what will be the angle theta? Okay, so from the simple SOHCAHTOA that we know from Pythagoras theorem, we know that tan of the angle tan theta will be equal to the opposite over the adjacent, which is the x of the angle, okay. So now this means that our theta is always equal to tan inverse of what? Y over x, okay. So these two are the things I want you to keep in mind, that always the length or the modulus, if you meet modulus, they are the same, of a complex number is the square root of the real power squared plus the imaginary power squared, and then the angle or the argument of the complex number is always equal to tan inverse of, or the arctan of y over x, okay. So these two equations, just keep them in mind, okay. Okay, so that is it. Now let's solve some example and you would understand, okay. Let's solve examples. Okay, so if I have a complex number, say z being equal to 1 plus I, okay, now I have to, if you want to know the actual angle that it is making with the positive, sorry, it should be the positive x-axis, okay, or the positive real axis. So this and that, so is the angle that it is making with this side, only this side, okay. Okay, I hope you get it, only this side from here to here, that is the positive x-axis. All right, let me use another color so that you know, okay. So it's from here to here, the positive x-axis, okay, the angle that it will make with that. Now, sorry, Now with let me erase this one. Now with this complex number, let's try to find the angle and the modulus or the length. Okay, so let's see. The length or the modulus of this complex number is always equal to what? Square root of 1 squared plus another 1 squared. Okay, and this will be equal to square root of 2. Okay, now we are saying that the angle of this is tan inverse of y over x, or a over b. It can be like that, and this is equal to tan inverse of what? Our a is what? 1, our b is what? 1, and this is tan inverse of what? 1. So what angle? What is the angle that when you find a tan of which you get 1? It's 45. Okay, so it's 45 degrees, or mostly we put the angle between complex numbers in radians. Okay, so 45 degrees in radians is pi over 4. Okay, so just put this in mind. Now we are able to find all these. Okay, so what is the purpose of this one? What is the purpose of trying to find the argument and the length of a complex number? The actual idea is that if I can resolve a complex number, okay, let's see, if I have a complex number that can be represented on a right angle triangle. Please forgive my drawing because I can see they are not straight. Okay, if I can represent my complex number on the size of a right angle triangle, let's take it like this. Okay, and this is our x, or this is our a, and this is our y. That is a sorry. Well, what have I done? Now, so if I can represent my complex number on the size of a right angle triangle, say this, if I have a right angle triangle like this, of which we know we can represent the complex number using right angle triangle, where this is the theta and the horizontal axis is the x-axis, or the real part, and the vertical axis is the imaginary part. Okay, so this is from the Argon plane. Okay, this is from the Argon plane, and this will be this side, the hypotenuse will be what? Will be the length of the complex number. Okay, now if that is the case, then I can write y and x, or the imaginary and the real parts, as what? In terms of the angle and the modulus, or the length alone. Okay, so from Pythagoras theorem, we are saying that tan of theta is equal to y over x. This we know, this is what we use to find the theta. Okay, now you know that sine theta is equal to the opposite, which is y, over the hypotenuse, which is this. So this means that our y, or the imaginary part, can be written as what? The modulus of the complex number sine theta. Okay, we know that cos of theta is equal to the adjacent, which is x, over the hypotenuse, which is this. Okay, so this means that our x can be equal to, or can be written as what? The modulus of the complex number cos of theta. Okay, so with this, let the modulus of the complex number be equal to a certain r. Okay, if that is the case, let's move to a new page. And if we are representing the modulus of the complex number with, let's say, r, okay, we are saying that the modulus is what? r, and then from the previous discussion we said a, or the x, can be written as what? The modulus, which is the r cos theta, okay, and then b, which is the imaginary, can be written as what? The modulus, which is the r sine what? Theta. The modulus is just the r that we've represented with, okay. If that is the case, then this means our complex number that we can write as what? A plus bi can be written as a is what? R cos theta plus r sine theta, then I. Then from here you can see that r is in both terms, so I can factor r out. Sorry, we can factor out r out, okay, and make sure that our equation or our expression is in its simplest term. So r out, cos of theta, plus we can manipulate, we can interchange I and sine theta, okay, so plus I sine theta. Now this is our complex number. This equation and this equation, they are the same, okay, so this is equation 1, this is equation 2. This means that equation 1 is the same as equation 2, but equation 2, this equation is what we call the polar form of complex number, or polar representation of complex number. So if you have a complex number and you are asked to change to the polar form, just change your a and b to r cos theta and r sine theta, and then you'll be done, okay, where we know that our r is always equal to the square root of a squared plus b squared, and our theta is what? Equal to tan inverse of a over b. I hope this is okay. Alright, so let's take some example and then you would understand, okay. Now let's take the complex number z equals the same 1 plus I, okay, or let me say 1 minus I want to show something to you, okay. 1 minus I. Mind you, we said that our complex number should always be what? Like this, in terms of a plus b, okay, so z should be a plus b I. Now our a is what? 1, and our b is equal to what? Negative 1. Sorry, negative 1. Our b is what? Negative 1, okay. If that is the case, then representing the complex number given above in the polar form, okay, in polar form, this in polar form, we said we need what? Our r, which is equal to the square root of what? A squared plus b squared, and our what? Theta, which is equal to tan inverse of what? A over b, okay. Now if we can figure out r and theta, then our z will be equal to r into bracket cos theta plus I sine theta, okay, in the polar form. Then we will be done, okay. So let's find r. R is equal to the square root of our a is what? 1, our b is what? Negative 1. So 1 squared plus negative 1 what? Square, which is equal to square root of 1 plus 1, and that will be square root of 2. Now our theta will be what? Tan inverse of what? 1 over negative 1, okay, which is equal to tan inverse of negative 1, and this implies that tan inverse of negative 1 is negative tan inverse of 1, okay, from trigonometry. Alright, tan inverse of negative 1 is the same as negative tan inverse of 1, okay. So this will be equal to negative tan inverse of 1 is what? 45. But we said in polar form we normally represent our complex our angle in what? The radians, okay. So in radians 45 is pi over 4, okay, so pi over 4, okay. or 45 degrees. So then if our theta is equal to negative pi over 4, then this means that our z is equal to, what is our r? Is square root of 2, then into brackets cos theta, cos of negative pi over 4, and cos of negative number is the same as cos of the positive of it. Okay, so cos of pi over 4. Okay, then plus sine of what? Negative pi over 4. Okay, this is what we will get. All right, but in when it comes to sine and cos, okay, when it comes to sine and cos is an even function. That is why when you find the cos of a negative number is the same as the cos of its positive. But for sine, the sine of its of a negative number is negative sine of the positive number. Okay, so the whole of this can be written as z is equal to square root of 2 into cos pi on 4, then minus I sine pi on 4. Okay, so that is it for the polar form of this complex number z. Okay, I hope this is okay. All right, so if that is the case, then let's move to the next topic, which is very, very interesting. Okay, now let's look at something. We said that complex numbers, something like z, which is equal to a plus bi, can be represented as what? This is equivalent to z, which is equal to r into cos theta plus I sine theta. Okay, if that is the case, then let's see. If I have z squared, what will be z squared? Z squared is equal to what? In terms of the polar form, okay, or you can even do it in this form, but let's look at the polar form, so that if you know the polar form of any complex number, raising it to any higher value will get a simpler formula for it. Okay, so z squared will be equal to the whole of this r into brackets, or let me multiply the r together. Okay, so r cos theta plus I sine theta. Let me write it again. Okay, you are saying that the whole of this will be equal to r into brackets cos theta plus I sine theta, all squared, everything squared. So let's put everything in brackets. Now from this will be equal to r squared times cos theta plus I sine theta, then times another cos theta plus I sine theta. Okay, so it's like you'll be expanding this. Now this will give me r squared into cos theta times cos theta is what? Cos squared theta, then plus plus I cos theta sine theta, then plus I sine theta cos theta. I'm multiplying everything, so I'm just multiplying this side to the whole of this bracket. Okay, then plus I sine theta times I sine theta is I sine theta squared, so it becomes I squared sine squared theta. Okay, then I'll close the brackets. How you can see, now this is equal to r squared into cos squared theta plus, look at something here, this side and this side, they are the same. Okay, so if they are the same, then it means I should pick one of them. Okay, so I should pick just one and multiply by 2, so it become 2I cos theta. Or let me write the I first. Okay, let me write the I first. So become plus I 2 sine theta cos theta, then minus, cos I squared will give us what? -1. We've done this in a previous video. Sine squared theta. Okay, this means that we will get r squared into cos squared theta, minus sine squared theta, then plus I2 sine theta cos theta. Okay, so this means that z squared in terms of the fuller form will be equal to this. Okay, but now look at this, but cos squared theta minus sine squared theta from trigonometry is the same as cos 2 theta, and 2 sine theta cos theta is equal to sine 2 theta from trigonometry. Okay, please kindly forgive my handwriting. Okay, if that is the case, then it means z squared would actually now be equal to r squared into, this side is cos 2 theta, so I get cos 2 theta plus I sine 2 theta. This is what we've gotten. Okay, but initially z was equal to what? R into cos theta plus I sine theta. So what is the relationship between z squared and z? Okay, you could see that when we squared z, the modulus of z, r, transformed to what? R squared, and the theta of it transformed to what? 2 theta. Okay, that is what we got. This means that if I continue, it is proven and it is true. If I continue to do z cube, okay, if I continue to do z cube, you can do this on your own and know that what I'm saying is true. If I continue to do z cube, this will be equal to r cube, then cos 3 theta plus I sine 3 theta. Okay, this is it. Okay, now it means that if I continue to any n, z to the power any n, I'll get something like z to the power n is equal to r to the power n, then what's cos n theta, okay, plus I sine n theta. So generally, if you have a complex number to a certain power, and then this is what the expansion will be, or the complex number expansion will be. So that is why we needed to know the polar form, so that if we have something like z being equal to, say, 1 minus I, okay, then z to the power 5, we'll be able to do this very simple, because if you are going to multiply this side by itself 5 times, this one, okay, let me erase it and show it here. If we're supposed to say this is equal to that, 1 minus I, 1 minus I, then to the power 5. You're supposed to expand this, then this would have been a problem. But since we know this formula, we just put it in and say, okay, fine, let's find our modulus of this. So R from this complex number, you got square root of 1 square plus negative 1 square, which is equal to what? Square root of 2. And now theta, which is equal to tan inverse of what? Tan inverse of the imaginary part, which is negative 1 over 1. So this will be what? Negative pi on what? 4. Okay. Then if that is the case, then our complex number can be rewritten as what? R is what? Square root of 2. Then cos of pi on 4, since we said cos of a negative number is the same as cos of the positive, so it becomes cos of pi on 4, then minus I sine of pi on 4. Okay. With this, we said that our z was equal to 1 minus I, and now this is the same as what? Square root of 2 into cos of pi on 4 minus I sine of what? Pi on 4. Okay. Okay. Now we said from the formula that we generated. Okay. I'll name. There's a name for the formula. Very soon we will state the name. Okay. We said if you have z equals r cos theta plus I sine theta, or in bracket, then z to the power n is equal to what? R to the power n cos of n theta plus I sine of n theta. Okay. Sine of n theta. If that is the case, then this complex number here, z being equal to 1 minus I all to the power 5 is equal to square root of 2 all to the power 5. Then we have cos of 5 times what? Pi on 4, which is 5 pi on 4, minus I sine of 5 times pi on 4, which is 5 pi on what? 4. Okay, so this becomes it. Now with this general formula, there is a scientist who derived the formula, and he's called Abraham de Moivre. Okay, de Moivre theorem. Okay, Abraham de Moivre. Okay, de Moivre's theorem. So this is what we call the de Moivre theorem in complex number. Okay, so the de Moivre theorem, like we said, z is always equal to r to the power, z to the power n is always equal to r to the power n, then cos n theta plus I sine n theta. Okay, but in some cases, in the polar form, okay, we say z is equal to r, then cos theta plus I sine theta. Okay, but in some cases, okay, some books they will leave it like this: z equals, then a bracket like this, and r comma theta. Okay, this and this, they are the same. Okay, you just represent the complex number in terms of its magnitude and its argument. That is the angle. Okay, so that is it for what you call de Moivre's theorem. Okay, now let's look at the nth root of a complex number. What we've done, with the De Moivre's theorem. Let's look at the nth root of it. Okay, so if I have something like this, okay, say, how do I put it? If I have something like z is equal to, let's say, 1 plus or a plus bi, and somebody asked me to find the z to the power 1 over 3, this means that what, the cube root of what, z, or z to the power 1 over 2, which is equal to the square root of what, of z. How do I do this? So with this, I write a general formula for you. I'll continue from there. Okay, so if I have a complex number given and I want to find the nth root of the complex number, this, something like this, nth root of z, then this is equal to r to the power 1 over n. Okay, this is equal to r to the power 1 over n times cos of n, let's say theta, plus 2 pi k. I will explain why we are using the 2 pi, okay, over n for the cos side, then plus I sine theta plus 2 pi k all over n. Okay, the same thing. Okay, this means that we will get different complex numbers in terms of the nth root. Okay, now we are using 2 pi k before because for cos and sine, the period of cos and sine is what, 2 pi. Okay, 2 pi. So it means, let me raise, and it means that for every 2 pi, when you take cos and, this means that when you take 2 pi, for every cos and sine of anything, if it reaches 2 pi, or let's say cos of 0 is 0, cos of 30 is square root of 3 on 2, like that. If it continues like that, and let's say it reaches 2 pi, it will start again. Okay, cos of 0 is actually 1. Okay, so when it reaches 2 pi, cos of 2 pi is what, 1. So then it starts again, and the values will be repeating itself. Okay, so because of this, it means that if I have cos of theta, let's say theta plus 2 pi k, this is the same as cos theta cos 2 pi k, then plus sin theta sin 2 pi k. Okay, now this is the same as cos of theta. This is true for every 2 pi, okay, times some constant k, and k ranges from 0, 1, 2, 3 going, okay, like that. Now sine of theta plus 2 pi k is also the same as sine theta. Okay, sine of theta. Okay, let's see for every 2 pi k. Okay, so keep it in mind, just keep this is the main formula that I want to keep in mind once we have this. Okay, let's continue, let's move on. So now if I have a complex number, let's say z equals, let's say 1, okay, and I want to find, let's say, the most popular complex number that people find the cube root of it is z equals 1. That is what I want to explain to you. If I want to find the cube root, or if I say that z cube, let's say this is it, z cube is equal to 1, then it means z is actually equal to the cube root of 1. Okay, so finding the cube root of 1, where 1 is what the complex number that we are considering now. So you go to our Argon plane, plot our 1, the complex number at this side, the right side, let's call it w. W is equal to 1. And so if that is the case, then if you want to find the cube root of 1, is the same as the cube root of what? W. Okay, now being the case that we have w equals 1, then if I plot this on the Argon plane, and let's say this is 1, the complex number, the imaginary part is what? 0. This is the same as 0i. Okay, then this will be our w. The w would lie on the real part. Okay, x, this is w. If that is the case, what is the angle that w makes with the positive x-axis? Okay, it makes an angle of what? Theta equals 0. Okay, so now we know that the complex number, say w, can be written as r from our previous discussion. So r cos theta plus I sine theta, that is w. Okay, which is the 1. So let's write it here and then you understand. We said w is equal to 1. Okay, but w is a complex number. We want to find z, where z cube is equal to w, which is 1, and this implies that we have z being equal to the cube root of what? 1. Okay, if that is the case, we said we are supposed to change w in terms of what? The polar form, which is r into bracket cos theta plus I sine theta. Okay, now w being 1, r will be what? Square root of 1 plus 0, 1 square plus 0 square, which is 1, and so square root of 1 will be 1. Now our theta, we said the angle that it makes with the positive x-axis, that is the same as tan inverse of 0 over 1, which is 0, and theta will give me what? 0. Okay, so now theta is tan inverse of the real part, the imaginary part, which is 0 over the real part, and that will give us what? 0. So now if that is the case, let's try to find the cube root of this. We said if you have a complex number, say w, then the cube root or the nth root of w is equal to r to the power 1 over n, then into cos of theta plus 2 pi k all over n plus I sine of theta plus 2 pi k over n. Alright, you will actually prove this in our next video. I'll prove this for you. Okay, comments, just leave a comment in the comment section if you want to know how to prove this, and then I'll come back and prove it. Okay, alright, then if that is the case, if this is true, then we said k is what? Equal to 0, 1, 2, 3, 4. Okay, 3, 4, dot, dot, dot. Okay, now let me ask this. If I want to find the square root of something, the possible answers will be what? Z1 and Z2. I have to have 2 answers. Okay, if I want to find the cube root of Z, I'm just writing a normal thing. Then I'll get Z1, Z2, and what? Z3. So it means that the cube root of 1 that you want to find is actually, you get what? 3 answers, and that 3 answers depends on the values of k that we pick. Okay, so therefore our z, which is equal to the cube root of z, the cube root of w is actually equal to r is what, 1 to the power 1 over 3. The cube root of 1 is what, 1. Okay, so we won't write it, so let me write it. 1 times, then cos of the angle that we had, theta, was what, 0, plus 2 pi k all over what, n, and where n is what, 3. So let me put it here. Then plus I sine 0 plus 2 pi k all over what, 3. Okay, this is how it's supposed to be. Okay, let's see. With this, if that is the case, then when k equals 0, then we have our z1 being equal to, that's the first one that we choose. Our z1 will be equal to 1 times, so I don't write the 1. When I put 1 in place of k, what will I get? I will get cos of 0 plus 2 pi times 1, which will be 2 pi all over 3. Okay, then plus I sine 0 plus 2 pi, sorry, k is equal to 0. Okay, if k is equal to 0, then this is what you will get. If I put 0 in place of k, I will get 0 plus 2 pi times k, which is 0. So cos of 0 and I sine 0. Okay, now z1 will give us what? Cos of 0 is what? 1. Okay, and sine of 0 is 0, so you give us z1 equals what? 1. That is our first solution. Okay, now when k is equal to 1, k is equal to 1, now our z2 will be equal to, into bracket, we said 1 to any power is 1, so we don't write the 1 into bracket. Cos of is 0 plus 2 pi k. Okay, so is this, we are just putting them in this, cos of 2 pi k over n plus I sine of 2 pi k over n. Since our theta is 0, we just leave them like that. Okay, so this is it. So if I put 1 in place of k, what will I get? 2 pi times 1, it becomes 2 pi over n is what, 3. Then plus I sine 2 pi over 3. Okay, right now let's try to simplify this. 2 pi over 3, pi is what, 180, so 2 pi over 3, 180 over 3 is what, 2 times 1 is, that is 360 over 3, and that is 120, so it becomes cos of 120 plus I sine of 120. Okay, if I have this, cos of 120 is what, 120 is what, the same as cos 60. Okay, but this time the sign will change, so it becomes minus half. Okay, then sine 120, it becomes positive square root of 3 over 2i. I hope I'm correct, right? Okay, so that will be my z2. Now z3, we just put, for as k equals 2, we just put k equals 2 in place of this one, like we said, this side in place of this side. Sorry, we will just put k equals 2 here. Okay, so now let's go and put it there. So when k equals to, our z3 will be equal to cos of 2 times 3 becomes what, is 2 pi k, right? So let me put it there, 2 all about 3, then plus I sine 2 pi into 2 all over 3. Okay, all right, then this will be equal to what? 4 times 6 is what? 240. So it becomes cos of 240. Sorry, cos of 240, right? I hope I'm correct. I sine of 240. Now let's see. Cos of 240, is it the same as cos 60? Yes, they are the same, just that this time it is also negative as well. Okay, so this will give me negative half. Cos 60 is the same as cos 240, just that they are in the opposite direction, so it becomes negative. Then sine 240 is also the same as sine 60, but it will give me a negative answer. Okay, so negative square root of 3 over 2i. So we've been able to find the cube root of z being z cube equals 1, and we were supposed to solve this. So the actual thing was we're supposed to find z where z equals the cube root of 3 and 1. The cube root of 3 and 1 is what? The cube root of 1 rather. Okay, and 1 is what? A complex number this time. Okay, so with the help of the Moivre's theorem and the cube roots, we've been able to solve for the cube root of a complex number. Let's say, let me write it here. We had z cube equals 1, and then we're supposed to solve this. It means we're supposed to find the cube root of this, and using complex numbers we were able to find that z1 is equal to 1 and z2 is equal to negative half plus root 3 over 2i, and z2 was equal to negative half minus root 3 over 2i. So keep this in mind, and that is it for the solution of this question. Okay, that is how the explanation goes. Now let's look at something. From Taylor series. Okay, from Taylor series. Okay, e to the power theta is equal to 1 plus theta plus theta squared over 2 factorial plus theta cube over 3 factorial plus theta to the power of over 4 factorial plus like that. Okay, and we know that cos theta is always equal to, from Taylor series, is always equal to theta. Okay, it's always equal to let me see, let's try to so cos theta and cos theta is actually equal to 1 minus theta squared plus theta over theta, 2 factorial plus theta to the power 4 over 4 factorial minus theta to the power 6 over 6 factorial plus like that. And sine theta is equal to theta minus theta cube over 3 factorial plus theta to the power 5 over 5 factorial minus theta to the power 7 over 7 factorial plus like that. Now from these Taylor series, if I find e to the power I theta, then it means that wherever I see theta, I put what? I theta there, okay? So it becomes 1 plus I theta. I hope you get it. 1 plus I theta. Then if I put I theta in place of theta squared, I'll get what? I squared will give me negative, so I get negative theta squared over 2 factorial, then plus, or I to the power 3 is what? Negative I, so it becomes minus I theta cube over 3 factorial, then I to the power 4 is 1, so it becomes theta to the power 4 over 4 factorial plus the dot like that. Now I want to prove something, okay? What if I find I multiply sine of theta, okay? Let me pick another color. This side, this equation. What if I multiply this one, the whole of this, by I? Let's check and see. If I multiply the whole of this equation by I, then this theta side will be what? I theta. This will be minus I, and this will be what? Plus I minus I to the power 7. Let's continue this to the fifth one, and you understand, okay? If I continue to the fifth one, it will be like this side. It will be like I to the power 5, and I to the power 5 is equal to what? I to the power 4 times I, and I to the power 4 is 1, so it becomes I. Then I put theta to the power 5 there, so I'll get plus I theta to the power 5 over 5 factorial. Then it means that the whole of the e to the power I theta will be the same as summing cos theta and I times sine theta. Look at it. If I sum cos theta, this one, and I sine theta, here you multiply I by sine theta, it will be like this one that is here plus I sine I theta, and that is here, then plus minus theta squared over 2, this is here, then plus minus I theta cube over 3 factorial, that is here, then plus this, and it's also here, plus this one, and it's also, so it will continue like that. So this actually means that e to the power I theta is actually equal to cos of theta plus I sine theta. Now let's multiply some constants to the e to the power I theta. Let's say r. So if I multiply r by it, then this will be equal to r into bracket cos theta plus I sine theta. Okay. Now what does this tell you? This side. This is the polar representation of complex numbers. Okay, we said that a complex number z can be represented as some r times cos theta plus I sine theta. In fact, we said that this is just any arbitrary variable. Okay, that is, if I represent the complex number in a polar form like this, I can factor this out, and so it will look like this. Okay, so this means that if this is equation 1 and this is equation 2, then comparing both sides of the equation, you could see that the right side are the same, then it means that the left side will also be the same. So z can also be equal to what? R e to the power I theta. And this is what we call the Euler's formula. Okay, now let's look at some important equation generated by this formula. Okay, there is this special equation that is generated by the Euler's formula. Okay, let's look at it. The equation is this. We are saying that z can be represented as what? E to the power I theta. Okay, sorry, R e to the power I theta. Now let's look at a situation whereby we have, or a situation whereby set some r will be equal to 1 and theta will be equal to pi. If that is the case, then z will be equal to what? R into bracket from this equation plus I sine theta. From this equation, z will be equal to r is 1, right? So I just put 1, and that will be 1. Cos theta becomes cos pi plus I sine pi, and this will be equal to cos pi is what? Cos of 180, that is negative 1, then plus sine pi, sine of 180 is what? 0. So this will be equal to negative 1. So this means e is actually equal to negative 1 when r is 1 and pi theta is pi. Okay, so if I substitute it in this equation, okay, if I put it in, then it means negative 1 will be equal to r, which is 1, then times e to the power I times pi. And this, if I send a negative 1 to the other side, becomes 0 is equal to e to the power I pi plus 1. Then this means that 1 plus e to the power I pi is equal to 0. Now this is what we call the Euler's equation. This equation is very interesting because scientists or mathematicians are saying that you have some 5 important numbers that we deal with in our daily life. That is 0, 1, I, pi, and e. And these are all representatives of some numbers. Okay, for example, I is what? Equal to the square root of negative 1. Pi is some pi is equal to 180 in terms of angles. Okay, and e is equal to some 2 point something. Okay, so if that is the case, then that is the case why I'm saying that mathematicians are really interested in this equation, the Euler's equation. Okay, now let's look at last part of complex numbers and we'll be done with the complex numbers tutorial. Okay, when we're doing the polar representation of complex numbers, okay, we didn't do division. I didn't do this before because whenever you have a complex number, you can change it to normal Cartesian plane and do your division and go. Okay, now z2 will also be equal to r2 cos theta 2 plus I sine theta 2. Now if I'm doing division in polar form, okay, z1 over z2, I'm quoting the formula straight. This will give me r1 over r2, then into bracket cos theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Okay, so if you are told to do division in polar form, this is how you do it in complex numbers. Okay, so that is it for the complex numbers. Now, since we were able to write complex numbers in terms of e, I'm saying that z is equal to let me write it well. We are saying that from z, which is equal to r e to the power I theta. Okay, now if I want to find the logarithm of z, then the log of z, which is, or the ln of z, let me put it that way, will be equal to the ln of r e I theta. Okay, but I can write the whole of this in terms of log, thinking that the base is what, e. Okay, so let's use that one. So log of z is actually equal to log of r e to the power I theta. Now this means that log of z is equal to what, in terms of logarithm, properties of logarithm, this will be log of r plus log of e to the power I theta. Okay, now this will give me log of r plus I theta log of e. Mind you, we are dealing with the natural logarithm, so the base is what, e, and so it means that log of r plus log of e will be what, 1, since this is the same as log of e base e. We are dealing with base e here. Okay, so it becomes I theta. Now if you want to know the logarithm of this in every situation, or in all cases, then we need to consider the period of sine and cos. Okay, so this means that this can be written as log of r, since we are dealing with sine and theta, then this is the same I theta plus 2 pi k. Okay, where k is equal to 0, 1, 2 going. Okay, so this is it for logarithm of complex numbers. Let me explain some parts and you really get it. Now with this logarithm of complex numbers, when I write logarithm of z being equal to log of r plus log of r plus I theta plus 2 pi k, when k is equal to 0, I have log of z equals log of r plus I theta. Okay, and this is what we call the principal logarithm of z when k is 0. Okay, so let's take an example. Z equals, let's say, 1 minus I. Now you know that with this, we've done it before, theta will be negative pi on 4. Okay, so this means that our r is also equal to square root of 1 square plus negative 1 square. Okay, and that will be square root of 2. Okay, so it means our log of z will be equal to log of the square root of 2 plus I into negative pi on 4 plus 2 pi k. Okay, now the principal value of this is when k equals 0, so this means that our principal logarithm will be log of square root of 2 minus I pi on 4, since k will be equal to 0, and when you expand you get negative. Okay, so that is it for complex numbers. Okay, from our next tutorial video going, we'll be solving practice exams questions on complex numbers. Thank you, and don't forget to subscribe to my channel for more videos, and see you next time.